Okay guys, today what we're going to go through is a bit of a rehash or a bit of an intro on one-dimensional motion. Starting off with what a scalar is, what a vector is, what a scalar is, the difference between speed and velocity, acceleration, how that relates to forces, and how they relate to some sort of momentum change. Okay, so a scalar comes from scale or size, so it's just a value. It's just 4 meters or 20 meters per second. All right. A vector, on the other hand, is a size with a direction. That's the only difference between those two ideas. Okay, so we still use the same units, we still talk about the same sorts of things, it's just that one of them has a direction, the other one doesn't. So that's those two kind of covered. Velocity is actually defined as the change in displacement. So velocity and speed are kind of related, distance, displacement are kind of related. Velocity is actually defined as displacement over time. So basically going from one position to another over a certain time period. In this case here, the displacement can be negative or it can be positive, and we indicate which one it is just by the direction of the vector that we're talking about. So if you've gone from 10 meters to 20 meters and it took you 2 seconds to do it, well, we can work that out. 10 meters is positive, 20 meters is more positive, so you've actually gone that way in 2 seconds. That's our velocity. Alright, if we want to talk about acceleration, the acceleration is actually the change in velocity over time. So speed or velocity is the change in distance or displacement over time. Acceleration is the change in velocity over time. So it's the change in the distance or displacement over time. They're all related. So we can write acceleration as, or let's use the same numbers as over here. We can say that we've gone from 10 meters per second to 20 meters per second, and we've actually increased our speed, increased our velocity, so we've actually accelerated in the same direction of travel, which means that we've got an acceleration value of 5, but the units are different. I'll show you. These are meters per second now. Whoops. Okay, so because it's meters per second divided by seconds, meters per second divided by seconds, we've actually got meters per seconds divided by seconds, so the seconds become squared. In order for something to accelerate, it must experience some sort of force. So I'm going to swap colours so this doesn't kind of get too muddled. Newton's second law, law number 2, is to do with forces and acceleration. So we can say F equals ma. If you apply a force in a direction, you'll make something accelerate in a direction. You'll make a mass accelerate in a direction. Nice, easy ways to look at this. We can also say that stuff up there is still that stuff there. Force, we're actually going to make a mass change velocity over time. Now, some of you may have seen the link between this and this before. So the link between force and momentum, force changes an object's momentum. So you can actually have a force applied over a certain length of time will actually change the momentum of an object because it's sped it up or it slowed it down. So looking at the top line here, P, momentum, is P, sorry, it just is. So P equals mv, or P, change of momentum is mass times change of velocity, or if you look back over here, the top part of this thing now is kind of similar. What about if I divide both sides by time? And I'm going to end up with that. This thing over here is force. So, alright, so now we've got a force is equal to a change of momentum over time. Or, we rearrange. Force over time is a change of momentum. Now, the last part that I want to talk to you about is conservation of momentum. If I want momentum to not change, so change in momentum equals 0, two things are going to happen. We either need to have some sort of impact that miraculously happens over t equals 0 seconds, i.e. it doesn't bloody happen, or our force, external forces, in this interaction, our external forces are 0. So if we have a system where we've got no external forces, we're going to have no change in momentum, or momentum is going to be conserved. Whatever we had at the start, we will have at the end. And that's a vector, that's a vector. Did I miss one? Yep, missed one over here. And another one there. Sorry guys, keep picking them up. Alright, so that means if momentum's conserved, we've got no external forces acting. Direction, once again, is important. So if it's going to the right, direction is positive. If it's going to the left, direction is negative. So when you're adding momentums, you can say 10 to the right plus 5 to the left is the same as 10 take 5, or overall 5 bits of momentum to the right. We'll worry about the units afterwards, but I'll give you a hint. It's to do with mass and velocity, so kilograms, meters per second. You should be able to work it out from there. Thanks guys.